Hello everyone, welcome to this tutorial. My name is Sentinel-1. I'm a Google Earth Engine specialist. In this tutorial, I'm gonna show you how to detect flooded area using Google Earth Engine platform and Python API programming. At the end of this tutorial, you will be able to produce maps for before and after flood event, and you will be able to produce the differences between the before and after images. As you can see, you will be able to produce precipitation maps for the study area and monitor the spatio-temporal variation in the precipitation data using multi-temporal mapping technique. This tutorial is really useful for those of you who are interested to learn about the association between flood and precipitation. Let's make a new notebook in the Colab environment. So, first start with importing essential libraries. Import Earth Engine libraries like EE and GEE map. The next library, XEE, one of the newest one, is not built-in available in the Colab environment. So we need to import it like this. And the next library, Xarray, it's a best complementary library next to the XEE, allowing us to combine the image collection format with Xarray format. So Xarray as XR. Remember to import matplotlib.pyplot as PLT. Let's run. Colab is connecting to the server first, and then the code starts running. If you faced with any challenge during this tutorial, you can reach me out on my YouTube channel and put your comments there. And also the code link example is available below this video in the description box on my channel. So, all the libraries installed and imported. As soon as you see the successfully installed, you can go to the next step. Let's clear the outputs. Now we need to establish a connection between Earth Engine and Colab environment. From Earth Engine library, call the Authenticate first. Then go for Initialize. Enter your project name. What is the project name? Each Earth Engine account, including a project ID name. Go to the code editor environment, then project info. You can find your cloud project name. Copy and paste into your code, just like this. Just a moment, something's wrong on my keyboard, and I'm trying to restart the keyboard first, and then I will continue the tutorial. Yes, sorry for the interruption. So here is the project name and the next argument, OPTURL. If you search on the net about the XEE and Google Earth Engine, you will find a GitHub page including a detailed instruction about how to use XEE and how actually you can use it in different steps and converting satellite data from image collection into Xarray formats. The OPTURL address already available here. Just you need to copy and paste into your code. Let's run. Now Colab asks permission to have access to your Earth Engine account. The permission is granted by the user, like this, by selecting an account. In the next step, we need to use Earth Engine data catalog and functions to actually plot multi-temporal variation of precipitation in your region of interest. First of all, we need to identify the region of interest. In the previous tutorials, most of the time, actually a simple rectangle preferred as a study area. But now I'm gonna show you how to use the shapefile to select your study area. So, if you go to the Earth Engine Data Catalog, you can find the large-scale international boundary polygons, the simplified version. So, here we can import the countries layer and filter out the target country for the further analysis. Okay, first of all, I need to make a global map, a global base map layer. Create a new variable map from GEE map called the map function. Make a base map like train. Then run the map again. You will have a user interface after a few moments with countries labels. For example, in this tutorial, I'm gonna select the Iran, my own country, as the region of interest. So, just select your region of interest or your target country by drawing tools available here. In the next step, we need to have the point or the geometry created by the drawing tools as a variable inside the programming. So, create a new variable, for example, location, sets to, from the map, select draw last feature, just like this. Convert it into a geometry. Let's run. So, the location created, and then we can call the international boundary and filter it based on the target country. So, the target country is Iran. Let's copy the feature collection first, and then make a filter bounds based on the drawing tools already identified by the location. So, let's print the Iran. It's a little bit time consuming, but now you can see a new feature collection with one feature is available. If you go to the properties, you can see the Iran is selected. You can plot the shapefile on the map. It is really simple. Just we need to use the add layer. Add layer, import Iran, leave the visualizations empty, and let's run. As you can see here, the shapefile appeared on the map. So, in the next step, I need to call precipitation data and produce a multi-temporal precipitation spatio-temporal map. Why? Because the precipitation, specifically heavy precipitation, is one of the main or most important criteria in the flood events. So, before doing any analysis about the flood condition, I'm highly suggesting to you look into precipitation variations through the time. Make a new cell and then go for ERA 5 dataset available in the Earth Engine. The ERA 5 monthly precipitation data is available here. You can copy the collection snippets into the code. So, we want to use the precipitation data based on ERA 5 estimation. It is a simulated product integrated through the time and through the spatial and temporal dimensions. So, define a filter date. Actually, in the 2019, in the March and April, we have experienced heavy flood events in the southwest of Iran. So that's why I need to plot the precipitation variation through the 2018 and 2019. So that's why start date is 2018, the end will be 2019. Select the target band, go to the band information, and here the total precipitation offering the monthly sum precipitation based on meter unit. Copy and paste. I will show you how to convert it into millimeter in the next step. Then we need to clip precipitation data based on Iran boundary. Let me to convert it into a geometry format. Geometry. Now it's okay. Let's run it again. Nothing changed, but the type of the data converted from an image collection into a geometry. So make a loop structure using map, define a function using lambda. Each input considered as a x that is clipped based on Iran's border. Then copy the properties from input to the output. Property names. We need to have all the properties of input data for the output, specifically the date acquisition information. So let's make a print and make sure precipitation variable works well. So we have monthly precipitation from 2018 to 2019. It is better to extend to 2020 because we want to see the precipitation changes through the 2 years to compare 2019 with 18 and see how much PR changes through the time in this area. Let's run, and 24 elements is available. That makes sense. 1 precipitation layer per month. Now we have an image collection format. You can see how it looks like. If you have background experience about the Earth engine, definitely you have a lot of information about image collection, format, structure, properties, and bands. So it's like this. But now I'm gonna show you how to use the XEE and XEE and Xarray to convert an image collection into Xarray format, a multi-dimensional format that facilitates the process of data in the further steps. So make a data set for precipitation data, call the Xarray and use the open data set. The input collection is precipitation. Engine sets to EE, coordinate system EPSG4326, WGS84. So the pixel size or scale is based on a degree. 1 means 100 kilometer, 0.1 10 kilometer, 0.01 1 kilometer. So but remember that the ERA 5 monthly dataset has 27 kilometer. That makes sense for the climatological data. So let's set the scale to 0.27. That is actually equals to 27 kilometer. So the region of interest already Iran's border defined. So let's run. After a few moments, you will have a new data set. So, a new data set created. No longer image collection is available. Just here we have a multi-dimensional format. One dimension is time, another one is longitude, and another one is latitude. Here we have a 3-dimensional data that explaining PR variation through the spatial and temporal structure. And there is a variable total precipitation. We have PR or precipitation through the time, longitude, and latitude. That's actually the kind of format in the Python allowing us to apply the machine learning algorithm without any challenge, even if they are not available in the Earth engine. So it means that using Xarray format, you will be able to use the Python structure apart from the Earth engine for the further analysis. So here the dataset is ready, but I'm suggesting to actually sort all the data converted from a image collection into Xarray format. Sort them by time, latitude, and longitude. But the time is main one. Not really important for the spatial dimension. Just try to sort them based on the temporal dimension. Then multiply to a scale factor. As I mentioned earlier, the dataset unit is based on a meter. We want to change it to the millimeter. 1000 millimeter equals to 1 meter. So that's why we need to multiply the existing data to thousands to convert it into the millimeter. So the data set is updated, sorted, and the units converted. So let's print again. We want to plot the total precipitation. Let's select the variable name and then use the plot function. X-axis in the plot sets to longitude dimension. We have longitude, latitude, and time. Y-axis, latitude dimension. Call axis, time dimension. Call wrap sets to 6. We will have a multi-dimensional, multi-temporal grid structure at the end. So the call wrap means how many plots do we have in each row. For example, I'm gonna have 6 plots per row. So robust sets to true. And I wanna actually use the contour format structure, contour F. So, and that's it. Let's run. After a few moments, you will have a multi-temporal grid structure that shows precipitation changes over the time. You can use another color template. CMap, for example, I prefer blues. Let's run. Yes. Now here you can see PR variation through the time. So the darker area, higher precipitation, and lighter area, lower precipitation. As you can see, spatially precipitation distributed in the northern area, northwestern, and also the western area, sometimes highly increased. For example, you can see in the late of the 2018, in November and December, the precipitation increases. That makes sense. But it's actually the high precipitation rate is still continuing in the early 2019, that you can see very heavy precipitation pattern detected specifically in the winter time, at the end of winter. Here you can see for a couple of months in a row, very heavy precipitation actually affecting most of the areas in the western side of country. So that's why in this time, specifically in the March, we experienced a very heavy flood event in the southwest of Iran, in the actually Khuzestan region. So now here you can see how heavy precipitation occurs. For example, the average precipitation in Iran, the annual average is actually, at least for this area, is between 200 to 300 millimeter per year. But as you can see, in 1 month, the amount of precipitation goes beyond the 180 millimeter. That shows how heavy precipitation is in this month. In the couple of months in a row, we experienced a very heavy precipitation, more than what it is expected for a whole of a year. So now I will show you how to edit, how to do some basic edits or adjustments on the plot and get the export. The first part of this tutorial focused on precipitation mapping, because for flood detection or flood monitoring, having enough information about the precipitation pattern is necessary. So now I'm gonna actually increase the size of the titles and size of the labels in the map, and also the size of the labels in the color bar, and then show you how to get export. Because whenever you want to publish a paper, or whenever you want to print your research work, it is important to justify, or it is important to have a standard size for the titles, labels, and axes. So from the PL, let's bring the plots, the created plot, or assign it into the variable, and then we can make a simple for structure or loop structure for each plot that's already selected. From the plot axis.flat, I'm gonna get the each title and increase the size. So from each plot x.get set title, set a new title. I don't wanna make a new title, just I'm gonna get the existing title and increase their font size to, for example, number 15. Higher values, bigger actually size, font size. There is a typo here. Yes, font size 15. Now you can see the titles are bigger, and easily you can see the associated date for each plot. Then I need to increase the Y and X axis labels. X dot set X label, X dot get X label. So the font size, we want to have the existing label just with a new font size. X dot set Y label, get the existing one, Y label, and increase the font size to 15 again. Let's run a code. After a few moments, you can see the labels increased. Okay, the next is about the size of the latitude and longitude values, or the numbers. So go to tick params, and increase the label size to, for example, 15 again. For both sides, for both axes, just forgot to add the axis sets to both. Something's wrong. The label size is not recognized. Label size. Okay, the problem is solved, and now you can see the labels with the higher size, with the bigger size at least. So now we have a color map here, and the color map also, you can change the label and change the size of the color bar numbers. It is easier for the readers to understand about the range of the values and the unit of the measurement, because the unit of the measurement is missing here. So now for the plot, select the color bar and change the or set a new label. So the new label is precipitation with millimeter, and the font size will be, for example, 15. Let's run, and now you can see, yes, the new label with the unit of measurement. It is easier for readers to understand about the unit of the measurement. So this is millimeter per mount. Now we need to increase the number font size. Plot dot cbar dot label size. It was a label size or tick params. Yes, it was a tick params. Dot cbar dot tick params. Okay, now we want to increase the label size to 15 again. I think the axis is missing. The X that's missing. Yes, now it's increased well. And as you can see, we have precipitation data, a multi-temporal precipitation layer that shows the spatio-temporal variation of precipitation through the time. Let's actually get an export from the plots using save peak. Precipitation 2018 or 2019. Let's save it as P-Iran with PNG, and the next one is BB box inches, sets to tight, and the next parameter, yes, is DPI. 360 typically give us a good quality for the output that you can easily use in your thesis or in your research work. In the left panel, the precipitation layer is available. Click on the download and save it into your system. And now you will have a high quality map that shows the precipitation over your region of interest. Okay, that was the first part. In the second part, same as the example, I'm gonna show you what happened after this heavy precipitation, specifically in 2019. So, to do this, we need to define a new study area. So, a new study area, but this time not whole of the country, in the southwest of country. So, a new variable map number 2 created from GEE map, called the map function again, this time with satellite base map. Let's print the map number 2, and now go to Iran, or you can do this for your own region of interest, and not specifically this tutorial applicable on Iran. You can use it for all around the world, and I'm highly suggesting to use these studies, to use these examples for your own region of interest. So, in the southwest of Iran, there are a couple of agricultural areas here, and actually these areas highly affected after the flood event in this region. So, now I'm gonna actually make a simple and a small border for this area and show you how flood events happened, or how actually everything changed after flood events in this area. We have a new ROI sets to. From map number 2, just select draw last feature dot geometry. Okay, now we have a new variable for new rectangle. So in the next step, we need to call Sentinel-2 dataset here, because the Sentinel-2 is a SAR, an active microwave, and penetrate through the atmosphere and not affected by the cloud or atmospheric impact. That is highly suitable for the for example, flood event analysis, and for those areas highly suffering from the cloud situation. So another variable, Sentinel-2 created, Sentinel-1, sorry, make a tuple and copy the Earth engine snippet for Sentinel-2. Let's define the filter date and filter bound. The filter date is same. Dataset started available for 2018 and 2020. For 2 years, we want to actually make a monthly Sentinel-1 monthly radar dataset to highlight the flooded area for some particular months. Define a filter bounds based on the new ROI that is created. There are a couple of filters specifically recommended for the Sentinel-1 data. I want to show you how they are works. The first is list contains filters. List contains. So we need to call those Sentinel-1 data in which transmitter receiver polarization sets to VV or vertical band. So you need to have some basic information about the remote sensing concept. For example, if you don't know about the VV, meaning that you have not enough information about the remote sensing basics. That's why you need to study a bit more about the theory of the remote sensing to increase your knowledge. The VV means the type of the polarization in the SAR data sets, means actually electromagnetic radiation sends vertically and received vertically. That's why we have a VV style here. Another filter, Earth engine dot filter, is equal filter. We need those products in which instrument mode sets to IW. So, and another filter is about the orbit property pass. Earth engine dot filter dot orbit properties pass. The orbit properties pass, oh sorry, the orbit properties pass is a property, not a filter. Another filter is again the equal filter, in which orbit properties pass could be ascending mode or descending. So for this area, the descending images are dominant. So let's make a print to see how many images available. In the descending mode, 111 image is available. Let's check the ascending mode, because no difference between the ascending mode or descending mode. Just the thing is, we need to choose that or choose that orbit properties that is most frequent or most occurred in your region. So the ascending. So 279 elements is available. That's why I go with ascending mode, because more images are available. Remember that the orbit properties pass is really important, and you cannot actually combine ascending and descending mode together, because they have different geometrical structure and may have negative impact on your result in that case. So select the target band, that here is VV. Two kind of bands, two kind of polarization practically available in the Sentinel-1, VV and VH. VV vertical and vertical horizontal. The same polarized data set, actually VV, offering higher energy for the region of interest, and you can have a higher quality result using VV, at least in this tutorial. For the rest of the tutorials, definitely maybe we prefer to use another band, but for the flood detection, the same polarization is actually most preferred. So The Sentinel-1 with image collection format is available, but as I mentioned earlier, we want to get rid of the image collection and convert it into a Xarray structure. Dataset number 2 created. Make call open dataset from XR. This time for Sentinel-1, engine EE, CRS again, EPSG 4326. This is the same ID for all around the world that bring WGS84 for your region of interest. So the pixel size or scale, as I mentioned, 1 degree 100 kilometer, 0.1 10 kilometer, 0.01 is 1 kilometer. I want to reduce it to 100 meter because actually the 100 meter for my region of interest is enough, but you can actually increase the pixel size or reduce the pixel sizes to smaller values such as 13, but I prefer 100 because that's enough for my region of interest. Because when you choose actually an appropriate scale value for your region, that's highly speed up the processing, and most of the unnecessary information will be removed in the analysis. That is really useful tips. So another one is a geometry, that is ROI. So now we have dataset number 2, 279 elements available through the time, but it is too much because the dataset frequency is weekly, and that shows we have actually more images for each date covering a part of a study area. So I need to convert it to monthly format to overcome this issue. So let's sort the second data set based on time information and apply a very simple equation like multiply to 1. This is a kind of trick, that simple equation, that highly increases the speed of processing, because when you do a multiplication, a new data set created, and the new data set is no longer linked with the data set coming from the Earth engine. That's why we will have a higher speed in the next steps. So let's run. The sorting process may take 1 minute, sometimes more or less, depends on your region of interest and number of images you will have for the analysis. But after the sorting process is done, you can go for the next step with a higher speed of processing. So now the process is done, less than 20 seconds. So now I need to convert it into a monthly format. Take the DS and dataset number 2 and apply a resampling format. Convert it to the monthly and get the minimum value for each month, because the water bodies have lower values, lower scattering value compared to the rough area. For example, the water has the lowest value, and buildings or rough areas offering higher reflectance values. So when you get the mean, it means that you are getting the highest amount of water available in each month. So let's run the monthly format, monthly data, and DS2 monthly is ready now. Let's run. Now we have 24 images. So I need to select, as you can see in the PR data, the heavy precipitation, the consecutive months we had a heavy precipitation for consecutive months in the early 2019, and unfortunately the flood event happened in the March 2019. Now I'm gonna compare April and March together. The flood happened in the April, and I want to compare the April and March together to show the situation based on after before the flood event. So that's why we need two variables here, a before image. So from dataset number 2 with monthly format, so let's select time sets to 2019 2019 March 2019, the before image, then select the first image. You can see the before. So only one image available because it is a monthly format. So then the after one, the after event backs to 2019 April. The April is the after event. So yes, now the before and after, both of them are ready. So now we can do a visualization for before and after images. So from the PLT, call the fig and x, or create a variable with two components, fig and x. So you call the PLT and then make a subplot structure. I'm gonna have one row with three plots. So one row, three columns. The fig size could be different based on the number of the images and the size of the plots. But now I prefer, for example, 9 and 3. You can change it whenever you want. So in order to avoid conflicts between plots next together, call tight layout, and the width margin v pad, or w or width pad sets to 3, for example. Now you have more spaces between plots. Okay, plot number 1 sets to get the before image first and select the VV band and make a plot. X-axis sets to longitude dimension, Y latitude dimension, robust, true. The robust help us to get rid of the outlier values. This is the robust, and the next one is CMAP, for example grays. I prefer to use the gray color for the radar data. And X, we want to actually decide in which frame show the before layer. So X0, X1 or 2. So I prefer X0. Let's run, and here you can see the images, but the size of the figure is not really good. We can increase the width of the images. Now that's what it looks like for the area. So this image is the before 1 month before the flood event. So in the March 2019. So let's plot the after image. After, plot number 2 and axis number 1. Let's run. Now you can see that area without water bodies highly covered by the water in the most of the region. So that's why you can see the minimum value, the darker areas showing the water bodies, and most of these area covered by the water bodies because of the heavy precipitation that's already addressed in our data set. So Now in the next frame, in the next plot, I'm gonna show the differences, the flooded area, the differences between before and after. It is also really easy to do here. So now another variable flood created. Get the before data and calculate its difference to the after image. Let's run the flood. So plot number 3. So now the plot number 3, we will have the plot number 3, x number 2. Let's run. So this should be flood, and let's run again. You can see the flooded area actually highlighted with the white color. If you want to increase the contrast, you can set, for example, the minimum value to the 0 to get rid of the negative ones. So that works like this. Minimum value sets to 0, and now you can see the flooded area with a better quality. So let's make an output from this image. Again, call the plt and save fig flood.png dpi 360 and bbbox height, bbbox inches, sorry, sets to height. In the left panel, now you can see the flood PNG is ready. Save, and now the output is ready, and you have a high quality map that shows the before, after, and the flooded area with a good quality. So I hope you liked this tutorial as much as I did, and I tried to give you some insight about the flood detection using Python API programming and Google Earth Engine platform. I'm asking you to share this tutorial with all the remote sensing fans in all around the world. Thank you for your attention.